But we are just halfway, right? Because
thank you very much, and it's a great honour to be here, and it's quite overwhelming to hear my career read out to me in such a thorough way. And thank you also for your patience. When I first arrived at the room with my team a short while ago, I thought you were all here for the previous lecture. So I'm really pleased you're here for my lecture, and thank you so much for your patience as we got the technology to work. So what I'd like to do today, I don't have to go through my CV because you've heard it, but what I'd really like to do is explain the European Space Agency to you and give you some of the science highlights. I'd like to actually do a quick survey. Hands up who are students in the room. Keep your hands up if you are physics, maths, astrophysics, engineering. Wonderful. And you will all be using, or will go on to use, or will go on to develop, or will work in industry, or will do science, I'm sure, with our missions at some point in the future. And I've had a wonderful lunch with some of your professors, and I've heard about the research that some of you are doing and some of the courses here, and particularly the design of the space science and engineering education system in Hungary. So it's a huge privilege for me and my team to visit. This is part of a tour of 22 of our member states that make up the ESA family. These are the ministers of our 22 member states, and every 3 years the ministers of these 22 European countries come together and they set the budget for the European Space Agency. And in 2022, just shortly before I was announced as the new Director of Science at ESA, there was a record ministerial settlement, and so we had a 17% uplift in the budget, and this showed how much collaboration and cooperation we have across our 22 countries, of which Hungary is a key member. And I think that for me, having worked in UK government, having worked in academia, having always collaborated internationally, and I have friends around the world through my research, this for me is a very hopeful photograph, because whatever our geopolitical climate is, whatever our individual political differences are within our countries, we're able to come together and think about something bigger than our national problems. And the fact that these ministers, with all of their challenges, the cost of living increase, the war in Ukraine, all sorts of other things post-pandemic, were able to come together and see the value of investing in space for the growth of our scientific frontiers, for our engineering, for the growth of our companies in our member states, and how we can do more when we come 22 countries together than when we operate alone. This for me is a really inspiring photograph. The science programme received a 13% uplift, which again was very, very positive and very welcome. And I hope today that I'll give you a little bit of a flavour of the incredible missions that we have had in the past, that we're flying currently, and that we will be developing in the future. And maybe you'll see a little path for how you might be part of this incredible journey. This is just a split of the budget. When the European Space Agency was founded in 1975, it was formed from two organisations, an international research organisation and a launcher organisation. So this was really the birth of satellite industry and the satellite business. So scientists wanted to go into space. There are some times we have to go into space for some things, and there are other times when it's better to go into space. And of course, the other part of that, we can't go into space unless we have a rocket to go on. And so this was really the founding of the European Space Agency just under 50 years ago. And one of the pillars of that foundation really was the mandatory budget. So every member state agreed, at that point there were 11 founding members, they all agreed to pay a percentage of their GDP into the budget of ESA. And that has persisted through to the present day. Every member state that joins agrees to pay that mandatory fee. And that is what funds the fundamental science programme within ESA. You can see this, the blue segment in the top left-hand corner. This is the 5-year budget. So we have 3 years, and then we renew our budget every 3 years. 5-year indicative budgets renewed every 3 years. This is really important for the stability of the programme, because the missions that we develop, we start with brilliant ideas within the science community across all of our member states. It's very much a bottom-up programme. And our scientists compete, and they compete really heavily because these are very oversubscribed programmes. And when the best ideas come through, we then actually have to invent the technology and the engineering in order to realise the scientific answers. And it's important that we have long-term stability, because some of our missions take 15 to 20 years to develop and to launch, and then another 10 years to develop the science. So these are lifetime level missions. And we really cut across everything, really. We have world-class science. I sometimes hear colleagues saying, well, maybe we can be, in Europe, we can be third after the US or China because of the investments. But actually, in the science programme, we're world leading. Our missions are unique, and they are world leading and internationally excellent. We need to drive technological innovation, because, as I say often, the technology has not yet been invented for us to actually address the science questions, and you'll see some examples of that shortly. And we also need each of our member states, we need to support them and help them to develop their industrial capabilities, because the way that I deliver my missions on budget and on time is by having proper industrial competitions. And so one of the conversations that we've been having here this morning is about how to support Hungarian industry and how to harness the excellence that you have in your industrial base, and how your ambitions for the future can be realised to help us all deliver a better science programme. The other thing that's also really important for us at the agency is the sustainability both in Earth and space. So one of the other major programmes that we have within the agency is Earth observation. So the science programme is everything above the Earth's atmosphere looking outwards, and Earth observation is looking downwards. And of course the satellite data that we have studying our planet is critically important to help us understand climate change and how to mitigate that, and also how to do disaster remediation. The other thing that we find important is to actually have some sovereign capability within Europe. Our Director General, Joseph Aschbach, has spoken very eloquently about what we're calling at the moment a launcher crisis, because we need to have our sovereign capability to get into space. And we had a very successful hot fire test of the Ariane 6 rocket, which is the successor to the Ariane 5 rocket that we've used for 20 years, just a few nights ago. So for 8 minutes, the rocket sat on the launch pad and its engine burned, and it was a very successful test. And then, of course, inspiration, because these are generational missions. So many of the young people who will then do science with our missions are currently maybe not born or are in school, or indeed as students, as you are here today. As I say, it's a very diverse programme. We do everything from near-Earth heliophysics all the way out through the solar system, planetary and interplanetary science. We look at other worlds and exoplanets, right out to galaxies, cosmologies, and ultimately fundamental physics and the study of the nature of space-time itself. And again, I'll go through some examples. We have 3 different types of missions. We have L-class missions, which are L for large. We're not very imaginative with our names. These are kind of 1.3 to 1.6 billion euro missions. Again, built up from ideas from our community. The M-class missions are about a €500 million euro mission level, and the F-class are smaller and faster, and they help us to develop capability within member states. We also collaborate internationally, so we're very strong partners with agencies like NASA and the Japanese Space Agency, and also the Chinese Academy of Sciences. And we also run a programme for missions of opportunity. So if any of our member states have a nice idea, they want to develop some capability, and their science community comes together, and we can actually provide some support, both engineering and financially, to join other missions that other agencies around the world might be developing. And our goal really is to make sure that we can continue to develop this programme in a sustainable way far into the future. And there's also a programme called Prodex, where we actually do lots and lots of technology development at all scales with our member states, because our member states, so universities like yours here, actually provide some of the technology for the instruments to go on the spacecraft. So you may actually work with your professors to develop some technology which will ultimately fly on an ESA mission. Here you can see our solar system explorers, and so in the bottom are the missions that we've flown in the past, and all of these data are available in our archives, so we don't lose anything when these missions end. You're always able to go and gather those data and do new science with them. In the middle we have missions that are currently in flight, and I'll mention a couple of these in the talk. And then above we have missions that we have in development, and again I'll give you a flavour of those. Going further out, our cosmic explorers, everything from outside of the solar system to the edge of the cosmos and beyond, I think we now live at a very special time, because we are able to sense across the entire electromagnetic spectrum. Dean mentioned some of the work that I've done with the Square Kilometre Array and some of the ground-based facilities, and of course we work very closely with ground-based facilities, but for many of these parts of the electromagnetic spectrum, we have to fly above the Earth's atmosphere, because obviously the atmosphere blocks everything upwards of the optical, and although we can sense into the radio, the actual sub-millimetre and infrared, again, is done better from space. And this slide just gives you an example that gives you a real sense of the length of timescale that some of these missions are under development, that fly in the sky, that produce some science. So all the way back to 1990 with Hubble, Hubble celebrated its 33rd anniversary this year, and it's still producing world-leading science. It's an incredible mission. And our European scientists have played a major role in producing some of the highest impact papers that have come out of Hubble. And of course, that now has provided a great foundation for the James Webb Space Telescope, again, on which we're flying world-leading European instruments that are producing high-impact research. And so you can see this array of missions, some of which are in development, some of which are flying, some of which have been retired. And all of the data exist in the archive. These are the elements of a science mission, and I've put these 6 blocks down. This is particularly for the JUICE mission, but it's true for any of our missions. Obviously, we need a launcher, we need a rocket to go into space. The reason I'm showing this is because the nature of the rocket actually also has a fundamental impact on the way we design a science mission. It might be the amount of mass that we're allowed to fly. We may have a mass budget, and again, we may need to innovate our instruments there. The Ariane 5 rocket was incredibly powerful for us in a scientific way because it was such a beautiful rocket. It was so precise in its launch that actually all of the extra contingency that we put onto our spacecraft with things like propellant, when you launch particularly well and the spacecraft is released very nicely into its trajectory, the thrusters and the systems on the spacecraft have to figure out where the spacecraft is pointing to start with. And we have extra propellant to figure that out. But for things like the Webb Space Telescope, for JUICE, the satellite literally was released beautifully onto its trajectory, and therefore we saved a lot of propellant. So the Webb mission now will go on probably another 6 years or 10 years beyond the original design because of the precision of the launch. So the rocket has been very, very important for us, and it's the same, we hope, when Ariane 6 comes along. You see a photograph of a group of people there. That's a tiny fraction of the communities that make our mission successful. This happens to be the JUICE science team, but our instrument and principal investigators live out in the scientific community. They're the ones that really make the missions a success from the payload and instrument perspective. The wider academic community that then does the research with these instruments, our industry teams, and obviously our engineering and technology and science teams within the agency all work beautifully together to make these missions a success. We also have our own ground station, so these are radio telescopes that track both the satellites but also bring the data back down to Earth. And actually we're increasingly seeing a challenge because our data rates are increasing, so again we need lots of innovation there. We have a missions operations centre in Darmstadt in Germany. This you'll see is very important for complex missions like JUICE, and I'm very pleased that I'm head of the ESA facility just outside Madrid, where we host all of the mission data when it's finally archived. So as you heard, I joined the agency in March this year. A very special time to be joining the agency because I really stand on the shoulders of giants. And for me, it was a very, very busy first 8 months. A huge privilege to be able to go to 2 major launches. And the first one was just 4 weeks after I joined the agency over in Kourou in French Guiana. And it's JUICE, the Jupiter Icy Moons Explorer. I love the name, so we actually have a cocktail, a JUICE cocktail. So you can actually go and make JUICE cocktails and drink them. I haven't tried them, I'm not sure how nice they are, but I'm sure they're beautiful. And there's lots of science in the JUICE cocktails. This is a phenomenal mission, and the idea is to go to Jupiter. It's on its way now. We had a very beautiful launch on the 14th of April. We had a 1-second launch window. That's how precise that rocket launch had to be. We were over there. Mike Keeley here is my head of projects, and his team worked tirelessly to make sure this launch was successful. We had to postpone due to weather on the first day. It was due to launch on the 13th. And within 5 minutes before it took off, we stopped. And all the VIPs went, what now? And one of the senior ladies came on and said in French, many of our visitors didn't speak French. She said very quietly in French, script for today. I'm not sure if that was the exact translation. And we all went, we had the King of the Belgians there as well, and we all went, oh.
Excuse me.
Exactly. Everything was green and there was one red thing. But the very nice thing about that was the team had done everything perfectly. So everything was green apart from the weather. That was the only thing we couldn't control. So we scrubbed it for 24 hours, and then we waited for the weather, which was trending slightly better. The rain lashed down, and I believe even the local Kourou fire brigade went out with an axe and hacked off ice off the fuel lines and made the mission a success. So we launched on the 14th. It was breathtaking. I mean, if you've never been to a launch, I recommend it. I stood out on the balcony. We saw the rocket launch in the distance. There was clouds. We saw the flames. We went, oh, as it disappeared in the clouds. And then about 30 seconds later, a slow rumble started, and the rumble got louder and louder, and the balcony started to shake, and it was visceral, so that's the sound coming afterwards. And we could hear the rocket sound as it went over. We then followed the trajectory. Obviously, the rocket had to make its way out of the pull of the Earth, and we had to make sure that the spacecraft was delivered and deployed safely. The spacecraft had to then figure out where it was, and then it had to unfurl 85 square meters of solar panels. We had to acquire the signal, so the spacecraft had to say, hello, I'm awake, I'm safe, I'm alive, I haven't broken into pieces. Mike's sweating at the thought of this thing breaking into pieces. And it was really tense. If you watched ESA TV at that point, even the presenter was getting nervous. We had a half-hour window for acquisition of signal. And the chap saying, so it's still nominal, it's 10 minutes, it's fine. It's 11 minutes, it's fine. It's 12 minutes, it's going to be fine. It's going to be fine, isn't it? It's going to be fine. And then you actually see the signal coming. 3 sigma 4 saying, oh. Then there's a feeling of, wow, the satellite's alive, but we still have to get the solar panels open. So again, we waited with bated breath. The solar panels unfurled. We could see the battery being drained, and then suddenly the solar panels pointed to the sun and our spacecraft was powered. And then we cheered, and then we went for a celebratory lunch. But that's not where the work stopped. So we all celebrated, we got on our flight, we flew back. But then at that point, Mike's team then had to go through some very serious commissioning of the mission. And you'll see an example of one of that in a minute. But this is the whole spacecraft fully deployed, and as I say, it took the summer to, it took several months to get to that point. And the goal of the mission is something very, very fundamental. The mission is going out to Jupiter, and it's going to look at 3 of the icy moons of Jupiter. And these are the moons that Galileo saw over 450 years ago, and he pointed the first telescope of the day at Jupiter, and realised that the Earth was not the centre of the universe. It got him into terrible trouble because the teachings of the church at the time was that the Earth was the centre of the universe. He said, I cannot deny my eyes. I think he denied it, but allegedly on his deathbed. And as I say, we have big questions to answer with this mission, and obviously they were the top questions that got the mission selected, but also it satisfies a huge amount of other science. So it will actually help us to understand the Jovian system as a mini-solar system. We can't study our own solar system because we're in it so well, but actually Jupiter itself, with all of its radiation, with its particle fields, with all of the magnetic fields, it actually looks like a mini-solar system. So we can study that from outside. And we can also try to understand whether it's an archetype for other water worlds and other gas giants that are common among exoplanets. We're now starting to find many Jupiters around other stars. And so the Jovian system will give us a real key to that mystery. It will also help us to search for habitable worlds, because this is the first step in finding habitability in other worlds. Obviously, we want to understand whether there's historic life on Mars, and we have programs in the agency to do that, but we also want to understand about life elsewhere in our solar system and in our cosmos. And then finally, the other thing that the Jovian system will do for us, and the JUICE mission in particular, will be to study some of the particle physics, the magnetic field physics, and some of the particle and plasma physics around these extreme objects, which we see are universal in astrophysics. And since there are so many students in the room, I'm going to let you into a little secret. So if you're ever in a presentation like this and you find it really boring, you can say if you do, it's fine. And you have a little sleep at the back. If you wake up at the end of the talk and the speaker will say, are there any questions? And you let your professors ask a few questions, and then raise your hand and scratch your head and look intelligent, because you are all really intelligent, of course. So what about the magnetic fields? That's a good one. 9 times out of 10, the seminar speaker will say, oh, yeah, now that's a clever question. You've seen through my talk. I neglected the magnetic fields, or their future work, or they're too hard to measure. First of all, don't ever ask anybody from the JUICE mission what about the magnetic fields, because they'll say, you slept through my seminar. And also me, if I'm giving you a gamma ray burst talk, because that's what I care about, is magnetic fields. But magnetic fields are incredibly hard. We don't know the origin of cosmic magnetic fields, but we know they're important for all sorts of particle acceleration processes in the universe. So if you don't study magnetic fields, you should study them, because they're universal. The other thing we've discovered is really powerful is actually sticking a little camera on all of our spacecraft. So this is a selfie of the Earth taken by the JUICE satellite on its way to Jupiter, which is lovely for public outreach, but it also has some quite serious uses. So when we were commissioning the spacecraft after it was launched, we had a problem with one of these antennas, one of these booms that have to go out and measure some of the properties around the Jovian system, called the Rime antenna, and it was stuck. It was a little pin, it was a mechanical pin, and it was meant to fire, and the thing was meant to open up like a fishing rod, and it didn't. And so our spacecraft team shook the spacecraft, they heated it up by turning it to the sun, all terribly dangerous things that nobody wants to do. And again, I can see Mike blanching at the front here at the thought of shaking his beautiful satellite. But then it worked. And there's a camera of the Rime antenna deploying in space. Now, obviously, we have the telemetry of that. Our scientists and our engineers are watching the telemetry. The thing went out, it locked into place, it didn't bounce back. And this is obviously on loop. But to be able to see it also is a little bit of a comfort. So the team did an incredible job, and the mission is now past its near-Earth commissioning review. It's moved on to its science, and it's now done its very first ever deep space burn. This is the flight path. So again, there's a lot of innovation in this. Anyone who's studied flight dynamics, or if you're doing your orbital dynamics, or you're doing your in-body problems, this is a cracker. Anybody play Kerbal Space Program?
Yep.
Yeah, have you done this one? You should do this one. This is a good one. I'm not that advanced yet. My rockets keep crashing in Kerbal, but anyway, this is a good one to model. So we have a gravitational assist around the Earth-Moon system, we have one around Venus, and then we have several as we go out to the Jovian system, and we'll reach there in 2031. End of the mission is predicted to be 2035. We probably think 2036 now. And we think because of the beautiful launch, we'll be able to get down to within 200 kilometres of the surface of Ganymede, which of course is making our scientists phenomenally excited. The reason we have to do these gravity assists is because our rocket wasn't powerful enough to shoot us straight to Jupiter. But the benefit of this is we get to do some science along the way. Now, we're very good at doing flybys. This is another mission called Bepi Colombo. This is going to Mercury, and it's actually quite hard to get captured by the gravitational force of Mercury. It's the opposite to Jupiter. Escaping from Jupiter is quite hard. And so what we have to do is we have to do lots of mini propulsions. We have to do lots of little burns with our rocket thrusters to make sure that we can lose the energy of the spacecraft and let it slowly settle into the orbit of Mercury, round about December 2025, we hope. Our most recent flyby was June of this year, and each time we do a flyby, we gather data. And of course, we take pictures. And that's a real flyby of Mercury. And you just cannot beat these movies. So we have these beautiful pictures. We know that our spacecraft is doing well. But the other problem with Mercury is it's a very, very hostile environment. And this is the thing, when we develop technology for space, we are operating in the most extreme environments. The hottest temperatures, the coldest temperatures, the extremes of temperatures, high particle fluxes, radiation fluxes, extreme torques. All of these are extremes. And that's why when we push scientific experiments and we push the technology to do these, that's when we get the feedback back to our industries and back to Earth-based applications. And what we really want to do is actually be able to study Mercury in great detail. And we have lots of things we want to understand. We want to understand its exosphere. We want to understand all of the composition of this little body. We want to understand the impact of the solar wind and how all of this planet was actually formed. And there are already some beautiful measurements that are coming out that we're starting to get from our 16-instrument Bepi Colombo mission. And, you know, there are some really fundamental questions. For example, why is helium at Mercury so variable? We really don't know the answers to these questions yet. The other thing we like to do, I say, is work in extreme environments, and obviously the Mercury wasn't hot enough, and we thought we'd do the Sun. This is a mission called Solar Orbiter. It's a really beautiful mission. I think it's about 0.37 astronomical units from the Sun now. It will ultimately go to 0.29 astronomical units, so about the distance of the Sun that Mercury is. And we work very closely with NASA, so they have a probe which is called Parker Solar Probe, and we've been doing some observations in concert with them. This is an ultraviolet photograph of the Sun. You can see many of the flares. The big flares that we get from the Sun, of course, those stream of particles come to the Earth, they interact with the magnetic field of the Earth, they produce the aurora borealis. But what we really want to understand is that Earth-Sun environment. We want to understand the solar wind. It has implications for our planet, not least of all for beautiful aurora, but also impacts our satellites. And ultimately, it can actually cause problems for our ground-based electricity supplies. But this is the quiescent sun. And you might notice this is not a photograph. It might be too bright in here, but hopefully you can see that this is a movie. These are some recent images that a series of images that we took. It's speeded up a little bit. So every second is 5 minutes of time. If I did it on real time, then you'd be here all day watching it. But you'll see if you keep watching, and you'll see little flares coming up from the surface. There's one there. So these are not the big solar flares. This is just the solar corona bubbling away. It's producing the light, it's producing the energy, and it's ultimately producing the solar wind. The lovely thing that Solar Orbiter will do for the very first time is it will come out of the ecliptic, which is the plane where our planets orbit the sun, and it will start to look at the poles of the sun. And we've never, ever had a view of our own star in that way. So that will happen over the next few months and years. And what scientists have started to understand, the dark bits here are actually regions of cooler plasma with open magnetic field lines, so not the loops that take the plasma back, but actually open field lines. And what we've discovered really is this is the fundamental origin of the solar wind. So these are the particles and the radiation that streams from the sun and actually engulfs most of the solar system. And so for the first time we're now starting to really understand what we call these little jets or these picoflares that actually drive the solar wind. So this is the most detailed physics we've ever known of a main sequence G-type star. Now if we go to another famous icon, of course this is Hubble. The sun, of course, has an effect on the planets in the solar system, and Neptune is a destination we may be interested in to take missions in the future. And this was a recent result that came out from Hubble, which is really beautiful. So scientists have studied actually Neptune as a function of time. You can see from 1994 all the way to 2020. And what they found was that actually with long-term monitoring of the clouds of Neptune, with the Hubble Space Telescope and also some ground-based near-infrared imaging, that there seems to be a correlation between the cloud cover of Neptune and the solar activity with a peak at the end of solar maximum, although we're seeing a slight change in the correlation. And there are some ideas about what might be causing this, and it was never really thought before that Neptune had this kind of variability, but you can see how important the long-term monitoring is, the resolution of the Hubble Space Telescope, and also the fact that it's been flying for so many years. And that, again, is the legacy and the importance of these long-term missions, that we can start to see how the cosmos is changing over different types of timescales and see what it correlates with. So for the first time ever, understanding the impact of the sun on our distant gassy giant planets. So going to another extreme, this is a smaller mission. It's called Cheops, and the reason I wanted to show you this, it's a nifty little mission that our Swiss member states led with collaborations from other member states. And we flew that to look at a number of things. But the reason I wanted to put this slide in, because I thought, well, we now see what's happening to Neptune because of the solar wind. But this was a brilliant result that came out of Cheops about, it found 4 mini-Neptunes seen in tight orbits around parent stars. And if you were to ask scientists back in the 1970s or 80s, what's the chance of finding a planet around another star, they would categorically have said none. We'll never find planets around other stars. And now we're actually able to find hot Jupiters, we're looking for terrestrial mass planets, we're looking at mini-Neptunes, and then we're starting to study the physics of these distant solar systems, which is incredible. And Cheops is a small mission, it's not a big mission. Another really nice result that came out here, round about Neptune mass-sized planet, was this one. You might have seen this in the press. It was called the mirror planet, because the albedo, so the reflectivity of the surface, is so high, it's literally like a mirror planet, and it shines very brightly. It was found by one of the NASA missions called TESS, and it was characterized from the ground-based. And then Cheops actually watched eclipses of this planet around its parent star. 19 hours in orbit, so it's a really fast orbit. So we're finding this incredible richness of the physics of different planets and actually beginning to study the detailed physics of other planets similar to our own solar system. We're also able to study the moons. This is Mars, and again we have an exploration program in a different directorate where we hope that we will go and land on Mars and we will actually take some samples and look for life. But we have a mission that's been in the sky now for about 20 years called Mars Express. We've recently just extended its lifetime for a few more years, and we've been taking incredible measurements looking down at the surface of Mars and studying some of its other properties. But what we've been particularly doing is studying the moon of Mars called Phobos, and you can see Mars in the background. It's a bit distorted while I show you Phobos. So this is a neat little moon, and the reason we care about this is because we actually have a mission in collaboration with the Japanese and also with our German and French colleagues, and they will land a probe on this moon. So we're not yet landing on Mars, but we're going to land on the moon of Mars, and again look for its physics, its composition, and understand whether there are any signs of life and how it actually formed in this system. And so we're actually, what we've been doing with our Mars Express mission as it orbits around Mars, we've actually been doing some tomography of this neat little moon and trying to understand how its surface is. We don't know what the surface is made of, and obviously it's a little bit scary to land a launcher on it when you don't know what you're going to land on. So this topology has been very important, and we'll be passing that on to our Japanese colleagues to guide their mission, so that hopefully they can actually be safe when they finally land their MMX mission on Mars in the next few years. Another really nice mission that you might have noticed, NASA actually crashed in to this asteroid, Dimorphos, and we have Hubble Space Telescope pictures after the crash. And what you see here, we think, are lots of little boulders that came out from that crash. Now, we don't know whether those boulders, well, what we think, they were actually components of the body and that they've then been dispersed in the crash. They're about 1 to 7 meters in diameter, and they're about 1/10 of the asteroid mass. So they were likely part of the composition of this asteroid, and they've either been removed by the impact plume or shaken loose afterwards because of the seismic ringing after the collision. And we have a follow-up mission actually going out soon from ESA to study this system. And so, you know, JWST, Hubble, they've been incredible at actually showing us the nature of the cosmos. Nearby objects, our solar system objects, objects like our solar system around other stars. This is some beautiful web imaging from a colleague of mine in our team in science, Mark McCaughrean. This is the birth of a new star. It's called a Herbig-Haro object, and you can see material planning out, shock waves. These have been studied from the ground, but this is probably the best view of that material being spewed out ever. And Mark and his team have done a very nice study of this system. They've done spectroscopy, they've looked at all of the chemistry of this thing. So this really is the chemistry, potentially, of future life. I mean, these are the elements that ultimately form our planets and ultimately us as humans. And they're born in these incredible outflows from these star systems. He also found a kind of a nifty, of course he got onto the front page of Nature, which was very nice. And he studied this whole Orion area, but one of the things that he now thinks he's found in this system, this is just Orion if you look on the sky, is actually pairs of Jupiter planets. So this is a bit of a surprise. If we zoom in here, sorry, this is going a little bit slow. So you can see how exquisite the imaging. I'm just showing this actually because Webb Space Telescope images are just actually also very beautiful. But if we zoom in here now, you see these tiny little double stars. So not only can Webb see through the dust and gas that the optical telescope of Hubble couldn't see through, it now has exquisite resolution. And Mark's just been studying these little binary pairs. And if these are planets, they're Jupiter mass planets in pairs, which again is a bit of a surprise. So that might be a new form of planetary body. And obviously checking that the telescope doesn't have double vision. So we care very much about planets, and we have a couple of really important missions that are currently in preparation. They're not in the sky yet. Plato is a suite of 26 cameras. This is an engineering challenge because each of these cameras are already at the forefront of imaging technology. They have to be designed and built to be exactly the same as one another. We should have 8 of them built by the end of this year. So you can imagine how challenging that is. And we're building these all across Europe. Then they have to be brought together on the spacecraft and integrated to make one single instrument. So again, we're really pushing the technology in terms of the capability. And what this will do, it will go out and look for Earth mass exoplanets. So we're looking for Earths around other stars. In concert, we're building another mission called Ariel, and this will actually do a complementary thing to Plato. It will actually study the atmospheric chemistry and thermal properties of 1,000 exoplanets. And this now is taking the study of exoplanets beyond collection. So I think we have 5,000–6,000 planets in the NASA archive, but we'll now actually be able to compare the atmospheric chemistry of these planets with our own and really start to put our planet Earth and its atmosphere into the context of a wider cosmos. So again, very exciting, and that will be ready, we hope, for launch in 2029. when we launch Ariel, we'll also launch this nifty little mission called Comet Interceptor. So you've seen some of our small body satellites, but this is a really exciting concept. So we'll put these both in the rocket, we'll fly them both together, and then we'll release Comet Interceptor, and it will go out and loiter in space and wait for a couple of years for a comet to swing by. Then it will launch itself in space and chase the comet and go study the comet. So I think that's a thrilling piece of technology, and it almost sounds like science fiction. It's our first ESA F-class mission, so it's small, it's innovative, and we hope it will be successful. I wanted then to touch briefly on our sort of galaxy and cosmology science. So Gaia is a world-famous ESA mission. It's probably one of the most successful missions ever. And if you've seen any of the pictures, the very first picture of my opening slide was not a photograph. That was actually a dot-to-dot picture about 2 billion stars in our Milky Way galaxy. Every single point in that photograph is a star measured by Gaia. So it's an incredible mission. And what it's been doing is actually been studying a number of cosmological sources called quasars. So these are supermassive black holes, about 1 million to 1 billion times the mass of our own sun. We think they sit at the heart of the most massive galaxies in the universe, and they accrete matter. And when they accrete that matter heats up and it shines very brightly, and we see them right out to the distant edges of the cosmos. And actually Gaia, because it's been actually looking at stars in our own Milky Way, but it's also been finding these things in the background. So there was free science that the system was not designed for, but is actually very good because of the actual precision of the technology. And so scientists have used this to actually find these quasars. And the reason they come in pairs or in these 2 or 3 blobs, that's actually one quasar, but multiple images of the same source imaged through gravitational lenses. So great blobs of matter in the universe that is not radiating actually acts like a cosmic lens, and then we get to see multiple views. So that helps us to actually diagnose the cosmos. And so we see, a whole range of different things in our cosmos. And again, the Webb Space Telescope is providing some really innovative results. We're also looking at the very earliest galaxies, and what Webb is showing us is that galaxies were forming sooner than we expected. They're more massive than we expect them to be, so soon after the Big Bang. And they also have already produced massive dust reservoirs. Now, dust and the elements produced in dust usually form by being cooked in stars. So you need many generations of stars, and we expect them to evolve much later in cosmic history. So we're already finding huge amounts of dust in the early universe, which again is a bit of a mystery and a challenge for our cosmologists. And we can do spectroscopy, we can look at the chemistry of the dust, and it's incredible that this is way at the early edges of the universe. And you can see that this beautiful spectrum here, anybody who studies dust in the Milky Way or in the local universe could never imagine that we could have such a high fidelity spectrum at that distance. So very early on in the early cosmos, early evolution of the universe, we've already got massive stars producing vast amounts of dust and elements that ultimately form us. So the other big mission that we had this year was Euclid. We launched that in July on a Falcon 9 rocket in the US, in Florida. We have infrared and optical images on this spacecraft. We've crunched them both together. Again, it's a very compact design. And this is a real European first. So this material is silicon carbide. It's a real European lead. It's structurally very stable, thermally very stable, so stiff and thermally stable, which is very important when you want to look at dark patches of the universe without any radiation coming from your telescope structure itself. And so this was a team who'd finally integrated it. That's the spacecraft in the background. We stuck it onto a Falcon 9 rocket and a beautiful, pristine fairing that we're sure we kept very clean. And we launched it into a clear blue sky in Florida, very different to our Kourou launch. The launch went very well. And what we really want to do is understand the nature of dark matter and dark energy. So Einstein's equation tells us that matter and energy tell space-time how to bend, and space-time tells matter and light how to move. And that's the only equation we need. So I thought for the rest of the lecture we'd just unpack that. I think it's 10 partial differential second-order nonlinear differential equations. Should we just? No, we won't do that. But what we do know is that there are 3 testable predictions that came from Einstein's equations. The first one was that the universe is expanding, and we've confirmed that experimentally back in the 1960s with the detection of the cosmic microwave background radiation. The second is that black holes could in theory exist in nature, and we've proven that by detecting cosmic black holes, stellar mass black holes, supermassive black holes at the hearts of galaxies. Everybody finds black holes in all over the place these days. And the third prediction was that when massive objects collide, so black holes collide or neutron stars collide, they cause ripples in space-time called gravitational waves, and we've detected gravitational waves with ground-based detectors. So far so good. Einstein was right about everything. But one of the real challenges we have is that we now know that the universe is not only expanding, but that expansion is accelerating with time, and we don't understand why, the so-called dark energy problem. And so what Euclid is designed to do is really to take us from this beautiful measurements that we made with the Planck satellite, the ESA Planck satellite, where we know that the primordial fluctuations in the cosmic microwave background then evolved to produce the structures that we see in the present day like galaxies. But we actually only understand 5% of the universe. The rest of the 95% is dark matter or dark energy. So although we've got all these wonderful telescopes, we've got all this wonderful knowledge, I'm telling you about planetary atmospheres and quasars and supermassive black holes, it's only 5% of the universe. So what Euclid is meant to do is actually to follow up this mystery. We know from Webb that we're starting to see all this structure early in the universe. We know we have strong lensing, but actually what Euclid will do, it will use a thing called weak lensing. So we see galaxies, they'll be distorted slightly, they'll be orientated in certain ways in the sky. So we need something that has beautiful and exquisite precision in terms of its imaging capability. We also know that dark energy and dark matter are coupled in some unknown way, and we know from the Planck observations that we have sound waves in the early universe, and these acoustic peaks in the cosmic microwave background actually imprint on the structure of the cosmos. So just 380,000 years after the Big Bang, you get a cosmic bubble, so a so-called sound bubble, and those structures then grow with the expansion of the universe, and if we're able to image structures over a large enough scale with enough fidelity, we should be able to find these loops. These are not circles, they're actually spheres. There's a suggestion that this was the first one ever, discovered. It should play. This is the first one ever discovered from the ground. It's not going to play. Okay. So this was a painstaking set of observations of galaxies. So each one of these dots are galaxies. Each of them has their redshift or their position measured, and it looks like a bubble. So it's the first suggestion that there might be baryonic acoustic oscillations. And we know from the evolution of the Big Bang to the present day that dark matter pulls gas together. The gas shocks, it produces stars, and you start to form galaxies at the intersection of these filaments. And scientists using ground-based telescopes have tried to map this cosmic web. This just goes out to redshift of 0.14. With Euclid now, we will do a vast area of the sky, 36% of the sky, which is the whole of the extragalactic night sky, and we'll do that back to 10 billion years, back to redshift 2. And we'll be able to understand whether or not we actually understand dark matter and dark energy. And this just gives you a sense of one shot with Euclid. It's about 2.5 times the size of the moon. It's 600 million pixels in one shot. And I tried to think what that would mean for me to display an image to you today, and I think I would need 64 4K by 4K high definition TVs to let you see one image at proper resolution. So no chance, I'm afraid. But anyway, you can go onto our data portal and you can zoom as much as you like. We did the first Euclid science image release this month. I believe it went around the world globally. You may have seen it, on your news outlets, on your social media and your newspapers. And we looked at certain patches of the sky to try to show the power of the telescope. This is a galaxy cluster on the left. It's the Perseus cluster, it's very famous, and actually you can already see over this vast array of the sky that there's already a filament. There are about 1,000 galaxies in this cluster. I've picked this little corner here where you can see there's a whole pile of galaxies if you just zoom and zoom and zoom. And this will give you a sense of the beauty of the galaxies. About 1,000 galaxies in this cluster, and we can image all of them with exquisite detail and also take their spectra. We can zoom in to individual galaxies. We can just change the contrast because we have that fidelity. We can study those individual galaxies. You can see the dust filaments there. And in the background of this single shot image, there are 100,000 distant galaxies. That's just one shot. We'll do 30,000 of these over the next 6 years. And of course, it's not just the cosmologists who will mine these data to get the cosmology numbers out. People who care about galaxies will be able to do galaxy studies to great detail. People who care about early stage galaxy formation. So these are dwarf galaxies, the building blocks of big galaxies. And then, of course, you can zoom right into these and look at individual star-forming regions and the gas that's puffed out when new stars are born. You can look at local regions. This is the Horsehead Nebula, which is very famous, but this one shot was about an hour of data. If you did this from the ground, you wouldn't have this detail. If you did it with Hubble, it would take several weeks. So immediately we're starting to really scale up in a different way. This is a globular cluster, which is the oldest known stellar structure in the universe. It's in our own Milky Way galaxy. You do it from the ground, the stars are all blurred and merged together. Again, if you did it with Hubble, it would take many, many weeks. And for the first time, we're able to measure individual stars, the lowest mass stars in this cluster, all in one shot. And all of these stars are being held together in this ball by invisible dark matter. So we're even able to do cosmology in our own Milky Way galaxy with Euclid. And as I say, Euclid will now spend the next 6 years in a very complex survey pattern, autonomously surveying the sky so that our cosmologists can process an unprecedented amount of data split across 9 data centres in the US and in Europe. And ultimately, I think we'll probably come out with one number. So when you see the answer to life, the universe and everything, and it's the W number, and they tell you whether it evolves with time, please remember this talk, how much work has gone into that single number. And don't let anybody tell you it was easy. 21 countries involved, 300 science institutions, 2,500 scientists who all kept this image embargoed. Now imagine that for trust. We kept our nerve. We were about to reveal it in private to the ministers in a space summit and then to the public 15 minutes later, and our scientists kept this secret for us. 2,000 industrial personnel. We'll look at 8 billion galaxies. We'll pick the best 1.5 billion of them. Mission cost about 1.4 billion euros, so it's about 90 cents a galaxy, which I think is really good value for money. Other missions, just to finish, Envision is a phenomenal mission that Mike is currently taking through mission acceptance review. This will go to Venus for the first time. It will use the oxygen-rich atmosphere to aerobrake, to slow the spacecraft down so it can go into orbit, and we will study the Venusian atmosphere from the surface to the surface of the planet to try to understand why our sister planet has evolved in such a different way to the Earth, and we hope we never evolve to become Venus. LISA will actually go out for the first time ever for humanity. We will fly 3 spacecraft together. They'll be 2.5 million kilometres apart, flying in perfect convoy to make a single interferometer to measure the ripples in space-time caused when supermassive black holes collide in the early universe. Never been done before. We can't test it from the ground. We can test it as much as we can. But each of these spacecraft will have to be flown with such precision that the test masses on each spacecraft do not know they're on a spacecraft. So you can imagine how our flight engineers are working hard on that. And then in the 2030s, this will be the X-ray mission. So we will launch LISA in 2035. It will take 2 years to fly to its operating destination. And in 2037, we will launch New Athena. 50% of the normal matter in the universe is at a temperature greater than 1 million degrees, and we don't know why. New Athena will unsolve that mystery for us. Will solve that mystery for us, and will also work in concert with our gravitational wave detector and our other facilities on the ground and in space. And then in 2025, our ministers will come together again, and I hope we'll be able to convince them that we have incredible ambition for the future, and we'll be building on all of your ideas for the future. We hope that they will uplift our science budget and continue to give us that access to space that we want for humanity, and that we will go safely into 2050 and beyond. And thank you for your time and your patience with the technology problems.
Carole, and we again apologize. Now we know like a faulty cable, how big problem can be as a consequence.
So you have great humility for our engineers, because imagine this cable problem out 2 million kilometres away. You've got to check and check again. No problem at all.
For questions.
Absolutely.
So if you have any questions, please. Related to science program growth.
Let me start off with a very simple question.
That's always the hardest. I hate when I hear that. That's always going to be the most difficult.
The impact of that asteroid, you said that these boulders 1 to 6 meters across with 1 kilometer per second on velocity, all around the asteroid. Is this, it's a simple calculation, physically feasible, so you calculated the impact velocity, the weight of the probe, the kinetic energy, and the energy required to free these boulders? Is this physically feasible?
It is, but we can't yet distinguish between the two models, right? So we cannot distinguish between they were impact ejected versus later with seismic ringing. So our follow-up mission will hopefully study that, and we'll get more information from that.
But the energy of the impact was high enough to free all these bodies?
We think so, but again, if you put resonance in for the seismic ringing, then you get some amplification there. So I think we can't distinguish yet between that model.
I understand. You included many missions like Hubble and others which are mainly NASA-led or financed. All these had substantial ESA participation? That's
yes, so the way we work with NASA, sometimes they provide an instrument for us. So for Envision, for example, they will provide a synthetic aperture radar. For LISA, they will provide some of the technology, some of the optical bench technology. The way we've worked for things like Webb, we've produced 2 prime instruments for them, which are producing some of the highest impact papers. Actually, some of the US teams, the science that you see coming out of them, are being done on European instruments. So obviously, we don't have the budgets to fund a $10 billion mission, but actually, we have incredible instrument teams across our European member states. And so we were able to produce these instruments and then negotiate that as our contribution in kind. So we don't give the US cash and they don't give us cash, but we then fund our member states to produce the technology. We put that technology on those spacecraft, and together it makes a better mission altogether. And then it means that our European scientists have access to Webb and to Hubble. And in fact, we are winning, I think something like 1/3 of the time on Webb is being won in open competition through the web calls. So it's clear that by having the capability to develop those instruments and the science case that drives those instruments, our scientists are also competitive at winning time on the facilities once they fly through open peer review competition, because they've got a double-blind peer review system there. So we are competitive, and it also gives us extra leverage. So we get to do extra science with missions that we wouldn't build ourselves, and vice versa. So we have US contributions to Euclid, but it's a major European mission, and then there are US teams who will also work on that cosmology with us. So I think it's a really important thing to stop becoming siloed. We compete, I would say, and we cooperate.
So a couple of follow-up questions about the missions. First of all, especially the first few slides were very dense with information. Is it possible to actually get a copy of the talk so that we can benefit from that? I could not see, because of the immense amount of information, whether you listed LISA as one of the missions.
Yeah.
Was that?
Oh, LISA's, yes. So we're going through mission acceptance review for LISA at the moment. We hope that if our program committee approves it in January, that we will then go out to industrial contract in the spring, and we expect that mission to be launched in 2035.
I understand, but I have not been able to locate that on the slide, and I did not understand whether this adaptation is still, hanging in the air, whether it's
not hanging in the air. No, it's part of the process. So we've been going through the engineering studies. NASA's been working on their components. We're going through all of the memoranda of understanding, the science data management plan. So there are lots of processes that happen inside the agency in preparation for missions. So we don't just kind of build it and launch it. We have to make sure that all of our partners agree, that we have a way forward, that we understand that the teams are all ready to process the data. By going through mission acceptance review, we have an independent review of the engineering, the cost, because obviously if the review team said, oh, it's going to cost 100 billion euros, we wouldn't have a mission, because we designed to cost as well. So all of that gets reviewed, all of our partner contributions, and then all the scientists agree in terms of the science ground segment. So all of that is put in place. We then take that to our program committee, and if that's approved, then the mission is adopted, or we go to contract, and then we go through it.
Sorry, I missed that. The Euclid slide listed 21 countries being part of Euclid. I know that some Hungarian scientists are working on that, but is Hungary officially a member of this consortium?
I believe so.
Any other questions?
Somebody's got to ask me, what about the magnetic field? So please prepare it back for that way.
Nobody's sleeping right now.
No, good, okay, don't ask me. Yeah, please go ahead.
I saw in one of your earlier slides you had all the missions on ESA, and there was a gap now in sub-millimeter, and there might be a gap in the future in gamma rays. So will that come back, the suggestions post 2050 after the new machines are launched? Or is it something that is considered now because I'm not familiar with the new machines?
Yeah, it's a good question. I mean, the integral mission, of course, has been hugely valuable. And in fact, it had a bit of a crisis about a year ago, and the team were able to save it. I think it was literally minutes to save it. And we also extended its lifetime this year, its operational lifetime, because it has a very important role supporting the ground-based gravitational wave LIGO season. Yeah, I mean, as I say, our programme is bottom-up, and so it's really for the community to propose, and there need to be frontier science questions. So we don't build missions just to fill a spectrum gap, right? We have a big science question that we want to answer, and then the quality of the engineering ends up that the missions act like observatories, okay? So we haven't deliberately picked or not picked a gamma ray mission. We obviously have other things, sort of the X-ray, X-Men Newton again is very important. We've got GRISM with our Japanese colleagues. But yeah, I mean, I think it's really for the community to think about. New Athena, of course, is going to open up a completely new X-ray window there for us. So I think there's also something about the scientific community, the size of the scientific community, and the capacity for the scientific community to propose and exploit those missions. And the same our industrial capability to absorb it. So I think, you know, within Voyage 2050, obviously we will have other calls for M missions. We have 3 key themes for Voyage 2050. One is fundamental probes of the early universe, and so if there is then a mission that gets proposed that wins through the competition, it may or may not fill that gap if that's what the science remit is.
While others are thinking, I might have a question. Is there any plan B if Ariane 6 will be delayed for the launchers?
If I'll be delayed. No.
You never know.
Well,
for the cable, you know.
Yeah, we're working very hard, and I think we were all really pleased to see the hot test last week. I mean, I watched it live on YouTube like that for 8 solid minutes as the thing burned, and it was wonderful analysing the data from that now. So we're very hopeful of that. I mean, I think within our science programme, I guess we plan for all eventualities. And you know, we're looking at that launcher landscape, and you can see what we did with Euclid, because that was actually meant to launch on a Roscosmos Russian rocket, and obviously we couldn't plan for the Ukraine war. Our council decided that it was not appropriate to launch on a Russian rocket after the invasion, and so we then, at very short notice, we had a decision to make. And our Director General was very supportive of the mission going ahead because it was so important. It was 15 years in the making, and it was going to put the European community in a world lead for cosmology. And so scientifically there was an imperative to launch it. We scoped out a number of options internationally, and then we decided that the SpaceX Falcon 9 was the best rocket to launch it. But it wasn't ideal, and so Mike's team had to work hard in terms of collaborating with SpaceX to help make sure that the satellite was going to be safe and not shaken too much, because obviously these are rockets that launch telecom satellites. They're not too bothered, they launch them and it's fine, whereas Euclid needed really nice conditions. So the team worked under great time pressure to design the adapter, and then also to help SpaceX understand that we needed a brand new pristine fairing. What we learned from Gaia was that a little bit of moisture, once you go out into space, it freezes and you have ice. That changes the behaviour of your optics. So we did a lot of lab-based science in terms of surfaces, de-icing, decontamination, those sorts of things, and we wanted to make sure that we were going to give the spacecraft the cleanest possible environment. So again, that was, you know, real collaboration with SpaceX, because they had to learn to do things differently. So there was a strategic decision that the scientific imperative was so important, and the industrial components and everything that came together, that we found a way to launch. So there's always a way.
Thank you. Okay. Sorry. Okay, let's start with the ladies. And then
What about the magnetic field?
Well done.
That was a big one.
I don't know, it's for you to discover when you come and mine the data. Yeah, it depends which...
You invited us to watch a launch. How can I get involved?
Well, you come with a good question about the magnetic fields and we'll talk offline. Is there another question in that corner? Did I see a hand? Or 3 here? Okay.
You mentioned that the Voyage 2050 has 3 main pillars, and one of them is the fundamentals of the universe, and what are the other 2?
So we have a solar system explorer. We're hoping to go to one of the gassy giants. We're looking currently at the technology demonstrators for landing. I mentioned for JUICE that we will study the likely habitability of those icy moons, but what we can't do is land and take a sample, so we hope that one of those missions will be to do that. We're currently doing the science specification, the testing of the different environments of where might be the optimal destination, and we're also looking at the technology pathways, because we would need to develop currently unknown technologies, or technologies that we know we need that we don't yet know how to do. So we might think about in-orbit assembly, we might think about how we would land and launch back off the surface, where we would analyse those samples, would we return them all the way to Earth, would we have an orbiting lab? So these are the frontiers of technology. And the other one is really from Milky Way to temperate exoplanets, and so something possibly like an infrared Gaia, because Gaia has been so instrumental in really transforming our understanding of the formation and evolution of our own Milky Way galaxy. And so we're building on, I mean, the theme through all of this portfolio is building on the knowledge and experience that we've developed from previous missions. As I say, it's a bottom-up approach from our community, but it's not just scattergun. We actually are building and bringing on that knowledge and experience from generation to generation. So you see a real coherence in the programme.
You mentioned the unwanted consequences of the war in Ukraine. Now, ExoMars landing. Is there a decision about that? What will happen to that? It's kind of built, right? It was in the launch pad, and now it's cancelled.
Yeah, it's been an unlucky mission. I have a colleague here who's spent many years of his life on this, so Rolf is nodding in pain at the front. I think 3 times it's been ready to go and postponed. Yeah, we're currently in development for that, so this sits in another directorate, and the UK, I think now this week has announced that they'll add some extra money for the Rosalind Franklin rover. So we're hopeful that we'll move forward on that. I know Daniel Neuschwander, who was my director counterpart for human robotic exploration, is also speaking closely to his counterparts at NASA, because we also collaborate on the Mars Sample Return Programme. And so they're really talking about how they re-engineer that programme so that we can actually make sure that we have a really strong European programme for Mars. So yeah, fingers crossed the next time.
My question is about launching capability. I think what I would like to ask is, so Europe is going to have Ariane 6 for launching obviously these important missions, but does cost matter more than preferring our own launch capability? So is ESA open to open up more for SpaceX and sharing more of the costs, or the most preferred way is to push it towards the European?
Well, first of all, both. So it's not just Ariane 6. We are pushing to have competition across Europe because that's the way we think we drive quality and price. And so obviously the Italians are developing their Vega launchers, and we have a strong competition. And again, Joseph's been very keen on making sure that all of our European partners understand he's keen on competition. And I think that's important. What that does is it drives innovation, and it also does drive cost, because obviously cost is a component in our programme. We obviously look at capability, so there is also a fundamental design capability where we also have to kind of imagine what the launcher sector will look like 10, 5, 20, 30 years in the future, because we have things like mass limits, we have how will we design our missions? And so we are already thinking about that. And I mentioned Ariel and Comet Interceptor. So they will both launch together if there's an Ariane 6. If we were unable to get onto an Ariane 6, we could launch on 2 separate rockets. So we already think in the science programme in terms of how we build resilience in. And we've had great service from Ariane 5, we have great confidence in Ariane 6, but not all of our missions need an Ariane 6. And then there's a whole other sector that I haven't mentioned, the whole new space sector, the small rocket launchers, national capabilities, CubeSats. That's also a very vigorous sector, which I know is something that's very close to many people here. And that's a real capability builder for you to figure out how to do a satellite, how to launch it, how to do your science, and then how to scale it to these big missions. So there's a whole growing ecosystem across Europe. But I also think that European sovereignty is important, because we do live in uncertain geopolitical times. So to rely on another nation state outside of Europe, where we don't know what the geopolitical climate will be in the future, I think is a risk, and I don't think that we want to have that risk.
Is reusability key?
It is, yeah, and again, it's partly what the launcher companies are looking at the moment. They have some development programs, they already have some technology there. And if you remember my first early slides with the 6 boxes, sustainability and protection of the Earth is important. as well as zero debris, which we have a zero debris charter. Lots to think about. You see, we don't have an easy job. We try to do everything all at once.
Any other questions?
Yeah, Carole, I don't have a question about gravity, but more about the ability for Hungarian SMEs and startups to get out of the Earth's gravity and to successfully pitch and win contracts with ESA, given that they won't have sufficient working capital or the pedigree that would normally be expected for a successful bid. So what advice can you give them to allow them to contribute innovation to ESA?
It's a really good question. It's something that was a big topic of conversation this morning in a bilateral. So we have a mechanism called geo-return. So obviously each country contributes a certain amount of money. And for the science programme, we have to get that right for all 22 member states. For the optional programmes, it will be by subscription. So what we are looking at are instruments to help your ecosystem understand how to engage with ESA and also to help you to develop a national strategy. And the way we can do that is by helping the big primes who might win the contracts with ESA also think about how they enable smaller member states with developing ecosystems to contribute to them. So we have a number of instruments and tools that we use literally to engineer that. And what we did agree this morning was that we would work with our colleagues here to make sure that there is an industry day so that you can access and understand what we're looking for, how the system works, and you can then also find out who your friends are within your own country. Because what I found with these member state visits is it often brings components together of a particular country, people who don't normally meet one another. Sometimes you have to come to a strange event that's not usual to meet your neighbours, and I think that's really important. So one of the reasons I'm doing these member state visits is, first of all, to say hello, but also to understand what the capabilities are, what the gaps are, what the trajectory is, because what we really want is that innovation to come through, and as you say, those SMEs to start to become established companies that then are sustainable to be able to grow and to bid back, because that's how we get the virtuous circle. So yeah, it's a great question, thank you.
Any other questions?
Could you tell us something about how the ESA would like to participate in the Artemis program to go to the moon or doing some research there?
Yeah, so ESA has a major partnership with NASA on Artemis. We have our astronaut centre in Cologne where we're training European astronauts very successfully. And obviously we will have European astronauts who will launch with Artemis. We're also helping on some of the cargo development as well, because obviously it's not just sending astronauts, you actually have infrastructure that we have to develop. So again, that sits in the Human and Robotic Exploration Directorate, so we have a really strong programme there, both in terms of the robotic missions, things like ExoMars, but also the human exploration side. And again, that technology, we already have a strong pedigree in terms of the work that we've done for the International Space Station. So obviously we've had astronauts living and working on the space station, but we've also had a lot of things that go up and down. So basic things like waste units, and I mean, it doesn't sound very glamorous, but it's really critically important that you have that space transport ecosystem.
Do you know some time scale when European astronauts can go to the moon?
Soon, I hope. In development. I don't have a number, but none of those are confirmed yet, but we hope soon.
Mentioning astronauts, would you expect to have a more increase or a decrease in human presence in the space? So, meaning more robotic exploration or human attended?
But it's a good question. There are lots of debates about this. If you listen to Lord Martin Rees, you know, he says actually humans can do space tourism, but actually robots do science and engineering. But then actually when you speak to our astronauts, they're incredibly inspiring about their ambition to go, what they want to do when they go there. And I think there is that vision of, you know, a lunar base. I think robotic technology will be important, as it is on the ground, because there are repetitive jobs in risky places where you'd rather a robot did it. But sometimes there are things that humans have to do. And I think both of them complement one another very well. We have to make sure that our astronauts are safe, that they can come back to Earth safely. So we actually have to make sure that the robotic technology goes first. We obviously don't put a human on a rocket and say, go figure the moon out, oh, whoops, it didn't work, or tell me how it is in Mars. That's not ethical. So I think the robots go first. And obviously we've also got a lot of medical programs, because if you then want to think long-term human transport to places like Mars, we don't yet know how to solve things like muscle wastage and loss of bone density. So we also have an ethical role to make sure that our astronauts are safe and healthy. I mean, they're the pinnacle of human fitness when they train, and we don't actually want the space program to damage them. So there's a lot of research going on in that as well.
Let's say we are working on that track as well, with muscle waste. So,
Still any other questions? No? Carole, thank you very much again for your very inspiring talk, and I can imagine that one of the young students will pop up as a PI of the next science meeting sometime in the future based on your inspiring talk.
I hope so, and I should also say we have fellowships open, so please keep an eye on our ESA website, whether that's research fellowships, archive fellowships, short term, and internships, and all sorts of other training and job opportunities, so please keep an eye on our website.
Maybe to the person who asked how to see a launch, come join ESA and then maybe work on a project and then you're invited to the launch. Okay.
Exactly.
Thank you very much again.
Thank you.